how did I define transmission loss? Transmission loss was 10 log 1 by tau. We will come to that, but you can model this in this manner also, assuming an equivalent analog circuit. I am not really interested in this, because as we shall see, this is the theoretically derived formula. This is the theoretically derived formula, is this. So, 10 log 1 by tau. So, it would be basically tau we have seen was how much was it, rho c, 2 rho c divided by square, I also was there something like this. Okay, let us go, 2 rho c by omega m square, m omega square. So, 10 log 1 by tau would be 10 log 1 by tau would be m omega square, 10 log of m omega square divided by 2 rho c, which will be simply 20 log m plus 20 log f plus 20 log 2 pi minus same square. So, 20 log 2 rho c, right. So, this is the expression it would be. So, if I write this, it will come 20 log m, 20 log f, 20 log 2 pi minus 20 log 2 rho c, minus 20 log, because 1 over tau it was. So, this is what it is. That means, if I increase the mass per unit area, my transmission loss will increase, and it will be higher at higher frequency, right. And this is a constant term, because rho c we assume to be constant. However, what is observed is that this it follows this law, all right, but these coefficients are not, practical coefficients are slightly different. So, one can derive and show that it is related like this, but finally, practical equation is something of this kind. I will come to this, but I suppose I have a practical equation given here. Before I will discuss this. So, you see what if we take the full equation, complete equation over a large range of frequencies without neglecting damping, then and stiffness part of it, what is seen is that with frequency the transmission loss value shows, for we assume that frequency should that frequency should be sufficiently high, right. So, at low frequency it has been observed that actually stiffness k x, we have actually did not take the stiffness of the system also. Stiffness controls it at low frequency, which is not acoustic frequency generally. There can be some sort of a panel resonance because of the stiffness of the thing, k x spring behavior of the panel itself or the wall, and in such cases you might have transmission loss gets reduced. Transmission loss reduces. So, this is not zone of our interest actually, this is not zone of our interest. Acoustic related things are somewhere here, acoustic frequencies are somewhere here, and majority of the room walls will be somewhere here, right. So, that is why you did not derive it also, region 1 and region 2 we even did not derive. There this is called stiffness control zone, which is related to vibration of the wall if it is there, but not of our interest, related to acoustic frequency. Then in this zone actually we can assume, this frequency zone we can assume that 2 rho c over m omega is sufficiently large compared to 1, that assumption that we made, and we get something like is proportional to, as the mass increases transmission loss increases 20 log m, but the slope is not 20 log, 20 it is somewhat different we will see. But something else happens, that is called coincidence dip. It should have gone straight like this with frequency 20 log f, this should have gone 20 log f, it should have gone like this 20 log f. So, if I plot it with respect to frequency, I should have got 20 log f, but something else happens, it is called coincidence dip. It is actually at certain frequencies, higher frequencies itself, the bending wave of the panel might match with the wavelength itself or projection of the wavelength itself. That is called coincidence dip. In some case of it can bend the wall fixed on or some depending upon the support condition, hinge or whatever it is, it can bend. I mean, I should draw it like this, it can bend, or there could be bending of the other modes also. And when this kind of a relationship is there, lambda of the bending wave I mean is there to wavelength of the bending of the panel itself, right. It may not be visible, but it can bend, structural bending of the panel itself. Somewhere lambda by sin theta, lambda is that of sound, when it matches you find there is a reduction in the transmission loss, and that we call as, there is a reduction in the transmission loss, and that we call as coincidence dip. So, coincidence dip occurs at some higher frequencies. At frequencies, audible frequency range, largely most of the wall of the room walls shows mass law, shows the frequency 20 log f, or some with frequency it increases, and it is proportional to, transmission loss is proportional to mass per unit area. Somewhere at higher frequency there can be a coincidence dip, and beyond coincidence dip again it follows the same parallel path. So, there is a reduction of the transmission loss somewhere here, and beyond it follows the same path again, right. So, that is what it is. So, frequency multiplied by surface density, what is it basically, f multiplied by m is plotted on this side, and this is the reduction transmission loss values, they are given for certain types of material, various random incidents, then normal incident, and other incident also one can look into. The critical frequency is given by this formula. For various materials it is available. So, thickness h centimeter, critical frequency. So, for various materials this kind of tables are or is given by this formula, or such charts are available actually. So, you can find out where coincidence dip will occur, and this is given by velocity of sound, h is the thickness of the wall, rho is the density, E is the elastic modulus. So, one can actually find it out in this manner, some formula is available, c square approximately velocity of the sound divided by 1.8 h c s, velocity in the solid itself. So, velocity in the solid itself. So, therefore, you can find out where the coincidence dip will occur, and beyond that again it follows the mass law. Anyway, we need not consider too much into it, actually you can do detailed work onto it. Actually, an equation that is followed most of the time is 18 log m plus 12 log f minus 25. It was 20 log m if you remember, plus 20 log f minus, there are some minus term, all that equation. So, this is this is a practical equation, that is why I said that you can derive it, get an idea that is function of mass per unit area. As you increase the mass per unit area, transmission loss increases, but not 20 log m, it is 18 log m, and also as you increase the frequency it reduces, but not 20 log f, 12 log f. So, that is what is practically used, that is what is practically used. That is why the derivation of it is okay, you understand the physical phenomena, but I can't derive this from, this is more of empirical, somewhat semi empirical sort of, and you can use this formula for calculating out the transmission loss. So, for example, how it will be using, supposing I know the supposing I know this room noise, I do not want it to go to the other room. So, one way is you take a approximate formula, which I will give you again. I think there is an approximate formula, yes, 14 log m plus something, not here. There is another approximate formula which takes care of all average frequency, which is 14 log m plus some value or minus some value, plus or minus some value. So, this is good enough. So, supposing I know the critical frequency at which I should design. So, I can find out what should be the transmission loss, and remember for two rooms the partition wall, if I have to design for noise control, it was related to the TL of that room, that wall, plus absorption in the receiver room. I gave you a formula earlier. So, there the TL is required. So, you can obtain the TL here, and for various frequencies whichever is desirable, whatever with the frequency values. So, you can design the partition wall based on this formula. If you double the mass, so you will actually increase twice m. So, your transmission loss will increase by 18 log 2. Log 2 is 0.3, so about 6 dB. I mean less than slightly 5 point some dB. So, if you double the mass, it will be simply about 5-6 dB reduction. 5-6 dB reduction is quite significant, because intense. So you can use this in design, right. Okay. So, these are some of the formula, frequency and for various kind of materials, surface density, and this is actually the reduction that is there for various kind of materials. This is there. This is again some transmission loss values for against frequency. Beyond this is related to coincidence dip, where it would not change. In fact, transmission loss would be 6 dB for every frequency reduction, nearly 6 dB. After that, it could be 10 dB. Between some place there may not be any change because of coincidence dips and things like that, but it follows something of this kind, right. Some practical examples. Now, for double leaf wall, if I have 2 leaves and there is a air cavity inside, modeling this is fairly complex, right, but I am straightway given empirical equation for this class. So, this is given by this formula 20 log m d plus 34, d is the cavity width. So, I have one leaf here, another leaf here, this is the d cavity width. So, mass, total mass per unit area of the wall including this two, 20 log m d plus 34, right, 20 log m d plus 34. So, you see it is a function of d also. Now, we cannot go on increasing the mass, I can't make the wall thicker and thicker. What I can do? I can make same wall separate into 2 parts, put a cavity inside, it will increase this. This is another formula 14 log m 1 plus m 2 plus 24, transmission loss 14 log m 1 plus m 2 plus 24. This is average over all the frequencies, this is also average over all the frequencies. So, one can use this, you can take 14 log m simply for a single leaf scenario, plus this somewhere 24 to 2, it is empirical equation. So, you can actually use this formula to calculate out the partition thickness you want, because mass per unit area is known to you if you know the material.
The second formula is not considering the cavity.
Yes, but considering the mass here and mass there, again an empirical equation, right, again an empirical. Well, this 24 and 29 would have taken into account, 24 to 29 would have taken into account, so that's all. But this anyway is a better formula. You might get some more formulae somewhere, because it is empirical. So, this one can use for cavity, you can use, knowing the cavity depth, you can use this. So, this was related to transmission loss. Now, how do I control noise within a space? If it is generated inside, then I put a lot of absorbers. If it is coming from outside, from the next room or from outside, then I provide insulation, and qualitatively I can say I should put heavy mass, right. See, even if you are not accurately calculating, because there is so much of uncertainty of the noise that is coming in. If it is all random noise coming from traffic or something like that, I will not get same frequency all the time, I might know the frequency range, and therefore, there is empirical equations are good enough, right. Okay. So, if it is coming from outside, I put in insulation. If it is generated within, I put absorbers. But I do something related to planning also, that I will come in the later. But supposing it is structure-borne noise, it is in this floor, coming from a floor above or coming from another room, because some machine is placed on the structure, then I have to provide isolation between the machine and the structure, right. And let us look at how do we do it. Here we have advantage, as I said, because we know the frequency. So far we talked of airborne noise control. Let us look at structure-borne noise control, and I have a mass equipment which has got a mass, equipment has got a mass. This is an isolator which could be springs or some sort of resilient material like rubber pads or whatever it is. So, this is the isolator and this is my structure, the foundation or the structure, whatever we call it. So, basically this will be, you know, this would be actually this would be, since they are machines and I know the pattern of their vibration, isolation is usually for machines, structure-borne noise comes from machines, but structure-borne noise also can be random. We will look at that later on. Let us see the one which is known. So, the machine vibrates, it is the force it imparts, you know, the equipment that imparts its own mass. So, this is actually vibrating. So, forcing frequency is omega, let us say, and sin omega t is because most of the machines are periodic, reciprocating or, you know, cyclic sort of. So, they will be periodic again and they will be imparting the noise with certain frequency. So, that is the forcing frequency and I can possibly assume it to be f 0 sin omega t. So, that is the force which will come onto the mounting, right, equipment, and then when I have an isolator, it has got a machine on top. So, there is a static deflection. First the isolator will deflect. So, that is a static deflection and it will transmit this vibration somewhere there. So, it will transmit in some another, you know, whatever the frequencies we can find it out. So, we can write the equation of motion for this. So, structure-borne noise is controlled through isolation, that is what I am saying. Transmission of vibration from machine to the building, that is prevented, and such a system can be modeled as mass and spring system, neglecting the damping part of it, right, and single degree freedom system, as one would have done in vibration. Machine foundation design takes lot more complicated thing, but I am not interested in this, we are trying to only control the noise. So, we can damping we can neglect because it will further reduce it. Damping means some energy loss would be there. Supposing it is pores, in the pores there will be air motion, some frequency, you know, through there will be air motion, some heat will be generated. So, the viscous damping could be there, there could be frictional losses, and that is the damping basically. So, that would reduce further. So, but for noise control we model our isolation, like a spring. So, this is my mass, this is the spring. So, isolation is the spring and this is my structure, and we simply write this equation, m y double dot is equals to k y, that is equals to 0, right. We have not taken the forcing function. First we are trying to find out the natural frequency of the spring itself. Okay. So, complex root, this one if you want to solve it, it will be d square is equals to minus k, right, by m. Auxiliary equation d square, you know, I can write is y double dot plus k by equals to minus k by m, y double dot is equals to y, right. So, this will be auxiliary equation will be written as d square is equals to this. So, root of this one is, it will be imaginary, plus minus k m. So, root of this equation is I k under root m. So, my solution would be when I have plus minus I, a cos k m by t plus b sin k m by t. You differentiate it twice, it will give you the, you know, same equation back, you can write it. So, general solution is like that. Initial condition at t equals to 0, y is equals to y 0, that is the static deflection, and velocity is equals to 0, right. It is you know, like initial condition when it starts vibrating. So, it has gone to the extreme, it would, you know, the extreme end, and from there it will start. So, a equals to y 0, then if I put this condition here, t equals to 0, this will be cos 0 is equals to 1, this will be equals to 0. So, t equals to 0, y is equals to this. So, y is equals to y 0 and a is equals to y 0 and b, you know, when t is equals to, let us say, you know, at t equals to pi by 2, at t equals to pi by 2, y dash, that is if I if I take the derivative of this one and find out y dash y dot equals to 0, put these two boundary condition, I will get a equals to y 0, b equals to 0. You know, if first derivative of this one will be a sine, am I right, under root k by m t plus b under root k by m will come here anyway, and b under root k by m. Yeah, I can write that, but I am just writing it. It is okay for me at the moment, under root k by m equals to t. So, I am just trying to find out b. So, if at t equals to 0, y dot is also equals to 0, b will be equals to 0, because y dot, this is y dot. So, t equals to 0, so b will be equals to 0, right. This is what was trying. I differentiate this. This is y equals to this, general solution y is equals to this, and then put first differential of dy dt equals to 0, then I get b equals to 0. So, a equals to y 0, b equals to 0. So, my equation then becomes y is equals to y 0 cos under root k m by t, cos under root k m by t, right. So, y is equals to y 0 cos k m by t, and anyway omega n is k under root m. This is what, this is the frequency at which it will vibrate. This is, you know, this is equals to omega n. So, k omega, this is the natural frequency of the system, of the spring, because if I you know, this is nothing but this is equals to omega cos omega t. So, omega n t. So, this will vibrate if I put the spring, push it and release it, I mean just release it. So, it will vibrate at this omega n equals to k by n, and this is twice pi f n. So, natural frequency of the system I can find out from here. So, vibrational spring is simple harmonic with k by m as angular frequency, that we know, and when machine is installed on the mounting, I will have a static deflection, and this static deflection is k. So, if the spring stiffness is k, you know, static deflection is delta, spring stiffness is k, then mg mass of the machine into g mass b equals to k delta. In other words, if I know the static deflection, you know, I can find out k by m from this equation, because that will be g by delta. So, when I put in the machine, what is the static deflection, if I know, I can find out k by m. In other words, I can find out what will be the natural frequency of the system. So, if I know the static deflection, I can find out the natural frequency of the system, right. So, f n is 2 pi under root k by m, etcetera, etcetera, and you can simply, you can express it in 15.76 1 by delta, delta is in millimeter, putting g, you know, in appropriate units I get. So, if I know the mounting which I am modeling as a spring is deflection, when I have put in the load, that then I can find out static deflection, then I can find out its natural frequency. So, natural frequency is the mounting I can find out. Some ideas are given, delta as a function of omega n for various materials are known. For example, if I know delta for a cork board, right, correspondingly what will be, because it will depend upon its stiffness and, you know, like EI, modulus of elasticity and all. So, this sort of graph is given in National Building Code for various material, omega as a function of, I mean, you know, delta relationship depending upon delta versus omega, you know, these relationships are available. So, when machine is operating, it imparts force f 0 sin omega t, forcing function, right. It imparts vibration to the isolation periodically. So, then the equation becomes f 0 sin omega t, where omega is the periodicity of the machine vibration. Now, just look at, if it is omega n, same as my natural frequency of the system, it will simply amplify it. Like I was talking about a hammer hitting a pendulum at the same frequency, natural frequency of the pendulum itself, and then noise will be transmitted at maximum. But if I do it, my, you know, natural frequency and forcing frequencies are quite different, then obviously it will not transmit it will not transmit. So, you can find out the solution of this equation putting y is equals to a sin omega t minus phi, because there will be a phase difference. So, a sin omega t, put with this how we find out solutions of such differential equations, a sin omega t minus phi, and if I do that for y is equals to a sin omega t, I just put it y double dot would be sin again back with a minus sign and omega square. So, sin omega t minus phi, I just differentiate it twice. So, first time I do, I will get a cos omega a cos omega t minus phi, right, am I right? And then this will give me a square, a remains as it is, there is a minus sign coming because again sin will come back, and plus k into sin omega t. So, that should be equals to, if this is a solution, particular integral because of the forcing function, this must be valid, and therefore, I can find out this value of a. So, a is a, I can find out a, from this a I take common, I get minus m omega square plus k sin omega t must be equals to sin omega t. So, in other words, when phi is equals to 0, a is equals to f 0 k m minus omega, and I can get an expression like this. So, the a I can get expression in this manner. I will come back to this in the next class again at this point of time. So, I can write the general equation as y 0 cos omega t because of the natural frequency point of view, and this is for the because of the forcing function. So, earlier without the forcing function this was the case, and then we define something called force transmittability, force transmitted divided by exciting force, and this now is slightly different than what we looked into, because there we are looking at p t square by p I square. This is from the isolation actually, and we can derive from this, actually we can derive an expression for tau. So, what should be the properties of mounting, that we can find out. It is a simple case of vibration isolation. Case can be quite complicated in foundation design and things like that. So, I think we will stop here, and next class we will relook into the thing again.